Hello everyone, I'm Fabio Rossi, technologist at National Institute of Physics in Genova, in Italy. I've been involved in the FAIR project for 2 years in Spoke 6. With this presentation, I'm going to show you our tool for educational and outreach in a matter of AI applied to the high energy physics. But its application goes far beyond outreach and makes it suitable also for research as well. We decided to develop this tool because a typical system employs thousands of channels. Functions are shared across multiple servers and are fully optimized at low level, but are often inaccessible during experiments. For beginners, developing AI algorithms under such constraints can be very difficult. This tool can bridge the gap between theory and real acquisition systems, benefiting both teaching and research. The tool includes all the general concepts of a stream and readout system, same architecture, same functionality, and also the same issues as, for example, the bottleneck in data transfer. But with a minimal architecture and a clean separation of all its components, it is possible to clearly understand each one and support teaching. And the most important point is the ability to accelerate innovation and AI integration. The tool consists of a hardware part and a couple of software interfaces for control and monitoring. All nodes in this educational system are based on Raspberry Pi 4, a low-cost, credit card-sized microcomputer that limits system performance but not functionality. When combined with C code and multithreading, the OpenMP library, the Raspberry Pi 4 makes the system fully customizable and expandable. Highlighted in the slide the auxiliary part of the system that includes all the necessary accessories to establish a local network, such as an MQTT broker for message sharing and an NTP server with GPS for timing synchronization. Highlighted here the data path. Data path can acquire two sensors, devices that can convert gamma radiation to electrical signals. Then, two custom PCB frontends digitize the signals and stream events to the data reduction node. In this slide, the monitoring interface shows just acquired signals with a typical fast rising edge and exponential decay. Compression is performed using standard algorithms, gzip, xz, zstd, or AI-based algorithms, for example the autoencoder, in order to reduce the bandwidth and avoid bottleneck. It is possible to verify network bandwidth before and after the compression node. It can be seen immediately in the plot, the reduction between the yellow and the red line, for example. I said that this system can go beyond educational goals, and this is an example. We use it to evaluate our online data reduction algorithm with a couple of different scintillators, BGO and cesium iodide thallium doped. In the center of the slide, we can see a statistical distribution of the reconstruction error of the entire dataset. Signals extracted from the lowest part of the distribution, top right of the slide, as expected, are perfectly overlapped to the original one, the blue line. Just below, also signal with saturation. It is quite good reconstructed. It is at least recognized as a saturation. Except for this outlier, the mean square error is confined below 0.5%, a quite good result. Even for the energy spectrum, low left corner, original and reconstructed are quite good overlapped, with a compression factor of 10, impossible for a standard algorithm. Comparable results also for cesium iodide thallium doped, but with a compression factor of 8. Back to the data path, the two data streams are merged at the frame router, which builds frames based on timestamps and send them to the high-level analysis. Each frame, as you can see, contains all the signals with timestamp in between frame boundaries and represent the entire state of sensors at a specific time. Not very interesting with only two sensors, but crucial in real detectors with hundreds or thousands channels. and high-level analysis, such as finding coincidence between signals or applying AI-based analysis, build histograms, and store data. This is the typical output with different histograms for different level of triggering and elaboration. This is my conclusion. Thank you for your attention.